Thanks very much. First of all, thank the organizer for having me here. Also, I should thank Boston for filling in for me yesterday. Secondly, I should thank Boston once again for listening so carefully that he knows that any talk about Diophantine approximation should start with Dirichlet's theorem. Thirdly, I should thank him for taking heed of that advice and stating Dirichlet's theorem in the start of his talk, so that I don't have to. I'm not evidently not listening. And maybe this thing will. So the outline of the talk, I'll start talking about measure theories, I'll start talking about Fourier transforms of measures, I'll talk a little bit about discrepancy, I'll give you a main result, and I'll sketch a proof of it. I'll do some applications, and I will talk about some stuff that I've not talked about before, which is weird. So I can only make apologies for mathematics being weird. This is something I've been obsessing about for a while, and part of it is joint work with my former student, Jonas von Jensen and Alan Hayes. He's not my former student. So let's start off with Fourier transforms of measure. So if you take a Borel measure, then you just integrate that against an exponential. Now work strictly in real life. You get the Fourier transform. So nothing big. And a sort of informal version of the uncertainty principle will tell you that it's not difficult, it's not possible for the Fourier transform of a measure and the support of the measure to be very localized, I would say. So the support of the measure cannot be very localized if the Fourier transform behaves rapidly. That's what I'm saying. To be made more rigorous, if you think of the Fourier dimension, the Frostman's lemma in practice. What's Fourier dimension? For Fourier dimension, you need to restrict your class of measures slightly. You work with random measures to ensure that you don't have measures of finite support. And then you define this formula. Maybe. The point slightly. So the dimension is defined as follows. For any s in the interval from 0 to the dimension, you find that a non-zero and finite random measure with Fourier transform behaves in the way specified. And if you have a bigger S, no such measure exists. And if you apply Frostman's lemma, which I alluded to before, which I'm not going to state, you'll find the Fourier dimension of any set is always bounded both by the Hausdorff dimension. So the applications I have, I'm mostly interested in whether this exponent on the right-hand side in the definition is possible or not. Call it a Fourier exponent, even if it's not possible. This thing is running out of battery. So some known examples. So it's a very simple exercise in calculus, basically. Real analysis. Prove that the Fourier exponent of the Bay measure is 1/2. On an interval, different, more complicated set, Kaufman proved in 1980 that if you take a set of real numbers, 3, 0, and 1, whose partial quotients and the simple continued fraction are found above, that's okay. At least 3. This has positive Fourier dimension, to be extended to bounded by 2 as well. Disappointingly, Kahanen and Salem proved that the Fourier dimension of the Cantor is the third set, 0. I'll get back to that. It's something that annoys me tremendously. Unfortunately, it's true. Bloom extended another result of Kaufman and proved that if you take a set of new approximable numbers with a maximal Fourier dimension, so we call that these are the numbers. So it's x minus p over q. Less than 1 q to v, infinitely often. These are the new approximable numbers. It's a big set, and it's Fourier. These last sets we call Salem sets. So the Salem sets are the ones where the upper bound from the Hausdorff dimension is the same as the Fourier dimension. I'll return to this image. Now, before stating the main results, I want to talk a bit about discrepancy. discrepancy is a way of quantifying how uniformly distributed the sequence is in the interval from 0 to 1. Formally, what you do is you take any interval inside 0, and when you look at your sequence, you count how many little guys from the sequence that fall within the interval up to some big N. And then you subtract off the number you'd expected. And the sequence is uniformly distributed, modulo 1, if this discrepancy is little of 1, or of X. And relating this to the notion of a normal number, a number X is normal to base B, if the discrepancy of the fractional parts of each of the n times X is little. So, uniform distributed. And what makes all of this tick, for me at least, is the average Random. Here it is, the story gives you a way of estimating from above the discrepancy of the sequence in terms of what I want you to pay attention to is the exponential. Right. Let me just sketch a proof, and this is one of the joint start with assessing with applications afterwards. So there's a theorem which has presumably just been published. It should be out on paper anytime soon. You take a measure of course the Fourier exponent, eta say, and you take a sequence. And you suppose that you have this inequality satisfied. So whenever you sum the reciprocal of the distance between elements of the sequence is raised to the power minus the Fourier exponent in question in some block, so both indices from U up to B. This is less than or equal to 1 divided by the logarithm of the upper bound, and then a sum of some non-negative numbers. Just any sequence of negative numbers. So you just define it by weight. Then for mu almost every x, we have discrepancy estimate, which is too big to fit the side. And the cap subside is just the partial sum subside. If you look at it carefully, it seems as if there's a leading term of order root n times log n to the 5 halves. That's as it should be. Now if I take any old sequence of A's and just slap it into the theorem, I get an upper bound on the discrepancy of the fractional part of the sequence A and X. It's almost surely valid for my measure of positive Fourier. In particular, I get uniform distribution. Now, if I assume furthermore that the sequence is lacunary, I get a good upper bound on the discrepancy, which is of the form that I just mentioned. So there's a root n, and that's power of order.
I'm sorry. First, can be half greater than 0, yes? Can be mu equal half.
No.
Yes.
Well, there exists a nu. I can't choose my nu. Okay, this is an existential statement on the nu. So if I could get it to be 1/2, I would die a happy man. Okay, but if you have linearity, you get very close to 1/2. So then you get 1/2 plus a bit power. Okay, well, how do you prove a thing like this? We appeal to this result, which goes back to Rademacher, which tells you something about random variables. So you take a measure space, a finite measure space, or probability space, essentially take a bunch of measurable functions, probabilists, those would be random variables, and you take a sequence of real numbers that bound these guys, particular cases. Then you make an assumption of some partial sums of upper bounds, and then what I want to again pay attention to is this simple math just to apply find the right random variable and apply the average random through the big result and then use the corollaries. So then your random variables, these exponential sums that they recognize, right? So if you massage the average random quality for a bit, you will find that the discrepancy is bounded about by these particular instances. Then I just need that variance estimate, right? The second normalism. In order to apply the probabilistic one. And I just use the Cauchy-Schwarz inequality and the decay estimate from the Fourier. And it all comes out in the wash. It's simple enough to prove that. Now let's see what we were interested in. Jensen, Hayes, and myself. Was applications of this. The application we were interested in was the applications to the Littlewood conjecture and the mixed Littlewood conjecture. So if you just recall the Littlewood conjecture for now, this is what it states. So you get Q times infinity over the integers, you look at the distance to nearest integer of Q alpha and Q beta, you multiply them together, we multiply by Q for a measure, and we get something which possibly is zero. It's mostly zero. It's zero outside of the measure, outside of the set of households. I mentioned zero, but this was not the route we went down. And it's certainly true if alpha and beta are not both badly approximate by simpleness. I'll just recall to you the mixed Littlewood conjecture as well. So you take a sequence of positive integers, increasing sequence in which any term divides the next. And then you define a pseudo-absolute value on the integers by taking if you take any integer, you take the largest element of your sequence which divides, and you take the reciprocal. So let me just specialize again. So if I take the sequence D, it's a sequence of powers of a specific prime, then the d-adic pseudo-absolute value is in fact a proper absolute value, and it's the p-adic absolute value. Okay? So I think there'll be a talk on the p-adic Littlewood conjecture sometime soon. This is a special case of this. The mixed Littlewood conjecture states that, there's the typo, the limit as q tends to infinity of, now instead of taking q alpha, I just take pseudo-absolute value sequence, I slap it in here, and I'm hoping that this will. And again, this is absolutely trivial unless beta is badly approximate. There's bounded partial quotient. What did we do? Well, that paper, which is coming out just now, prove the following. We take a countable set of badly approximable numbers, and we take a countable set of divisibility sequences. So this could be all the p-adic. They're only counting in primes. And then we show that for a set of P consisting exclusively of badly approximable numbers, but with maximum household numbers, there are as many in a metric sense, there are as many elements in there as there are badly approximable. This doesn't mean that they're all okay. And then we can get into the many solutions to inequality, yeah? No matter which gamma we feel. So this is slightly stronger than the Littlewood. Of course, it doesn't hold everywhere. It holds most of the time. And also, we can get the mixed Littlewood conjecture. And if we assume that the ratios in my divisibility sequence are bounded, that's okay, for I, we get the same right-hand side.
I'm sorry, gamma. What is it?
Gamma is any gamma.
Any.
And delta is any delta. So this is true no matter which gamma or which delta you slap into the thing. So this is an inhomogeneous version. So if I specialize to the case where gamma and delta equals to 0, I get the usual Littlewood conjecture and the mixed Littlewood conjecture. But only in this mesh process. Right? So I've not actually proved the figures.
You mean there exists a set J of badly approximable number with maximal dimension?
Yeah, so there exists a set G, which consists of badly approximable numbers. The Hausdorff dimension of G is 1, same with the badly approximable numbers, such that for any beta in G and for any gamma delta in the interval from 0 to 1. We have the integrated solutions to the two things. Okay? I'll sketch how to prove it. So I'm just going to suppose that, just for the Littlewood part, I'm just going to suppose that we're going to fix an alpha. We're going to suppose that the set of numbers satisfying the conditions has Hausdorff dimension less than 1. But remember these measures that I claimed exist, the Kaufman measures. Right? The Kaufman measures will fill up the entire space, so I can pick an M such that the Hausdorff dimension of the set of points with partial quotients are bounded log by n has bigger Hausdorff dimension than G. This is because the set of badly approximable numbers has maximal Hausdorff dimension. I should thank Forsten for mentioning that yesterday. And I'll take the Kaufman measure, so the measurement badly approximable, satisfy this. And for one of these cubes, I'm just going to take the sequence of denominators of convergence. That's an actual sequence. And then I know that this sequence has the strong discrepancy estimate almost sure. Kaufman almost sure. And this gives you infinitely many solutions to the inequality for mu m almost all pieces. There's a mass distribution principle which works nice for the Kaufman measure, which will then contradict the first one. Okay. Let's talk about this result also. So this is a result of your Shapiro, a measurable result. So what he proves is that if you take a set of alphas and betas such that no matter which gamma 1 and gamma 2 you fill in, this inhomogeneous variant, the Littlewood conjecture, is true on a set of full measure. Now I wanted to get another proof of this. Right? But I couldn't. What I could get was proof of this. So what's happened here? I've shifted one of the inhomogeneous terms to the almost every side. But I've made the statement slightly stronger and improved it by a logarithm. Okay? This, by the way, is unpublished. It's on your slides. I can write it down at some point. The way to do this is to apply a converse to Fubini's theorem. Fubini's theorem, you know that sometimes you can integrate with respect to a product measure. It is a sort of converse to it. You take two measures and you take a measurable set. Inside the Cartesian product, it's null or full, if and only if almost every fiber going in one direction and the other direction happens to be null or full. But you need both. It's been called the cross-fibering principle by Haynes, Birzniewicz, and Milani. Then you also need a result of Kurzweil, which tells you if you take an error function, a decreasing function, such that the series of its values at integers is divergent, then for almost all alphas, the set of gammas for which this, what has been called recently, twisted inhomogeneous Diophantine approximation is satisfied. This thing is full with respect to the measure. So how do you prove the Shapiro result that I've classified? You fix an irrational number. Well, then you know that for almost every gamma there's a sequence such that this inequality is satisfied. The first corollary, simple corollary, tells us that for some nu, the discrepancy of this sequence is this gives you immediately this thing. I just took any only rational number, which is disappointing because I only need it for almost everything. So I know more than I actually use, which also annoys me tremendously.
I'm sorry, can you take the power in 1, 2, 3, 4, and to power epsilon? Can you take without 1 minus u? Can you take
Where do you mean? Yeah.
Post slide.
So what you want one?
Can you take 1 minus mu equal epsilon? Close to 0. 1 minus mu.
With the irrational number, okay.
For almost all beta. I
Yes.
think that discrepancy will be less than m to power epsilon for every epsilon. Positively. Without 1 minus mu,
Yeah.
epsilon. Therefore, mu close to 1. It can be close to 1.
But you want a better discrepancy estimate. Well, this is the discrepancy estimate I can get almost surely. Right? I'm not claiming that it's for specifics. I'm not saying for specific values of x.
Because uniform distribution of the sequence Q alpha is very well.
Yeah.
Therefore, we can be very close to gamma 1, very close, and different less than 1 over Q. And no, I'm sorry, later.
Okay. Then. And now the machine died. Go ahead. Okay. Well, then you consider the set from the theorem and just moving slightly more quickly because I think I'm running out of time. I can take fibers going in from one side and the other side. And the first cross-fibering thing follows from the preceding argument, so from curve fibers. The second cross-fibering is again easy. It's just an application of curve fibers. And this tells you that you get this sort of, in a sense, improvement and also, in a sense, much worse variant which occurs. Okay. Now we're into some speculation, stuff that I cannot do and stuff that just gets done. So I've called this non-uniformity in Shapira's result. But let me just give you some speculations of what you can see. So recall once again that Bloom's result tells you that the Fourier dimension of the set of new approximable numbers is maximum. And if you look at exponents of approximation, you take this uniform exponent. So what's that? Well, it's like the irrationality measures, irrationality exponents of the differential stuff. In this case, it's uniform. So what do I want? Well, the distance to nearest integer of q alpha minus gamma, so it's an homogeneous variant, should be less than x to the minus w, and q should be less than x. This should be soluble for all sufficiently large. And the result of Fourier and Roman, which is much more general than this, will tell you that if you have a new approximable number, then the Begel will surely in gamma. The inhomogeneous exponent is this thing. So note that it tends to 0, as mu tends to infinity. Now if you fix a nu and you take a measure supported on the new approximable numbers with Fourier exponent arbitrarily close to 1 on u. Doesn't it? Then you can adapt the argument from above to show that not with respect to the vague, but with respect to this new measure, supported on the new approximate number. If I measure alphas and betas with respect to this and gamma 1 with respect to the vague measure, this has maximum measure as you want. Now, because of the Peugeot-Long result, the two inhomogeneous terms, the Diophantine terms, will do their damage to be really, really big. So it would seem that you can make a uniform version of this Castle's conjecture, the Fourier result, fail spectacularly on a set of positive Hausdorff dimensions, but with a non-uniform version is likely to. So it's a bit of speculation. That comes out of obsessing with this for long enough. Now let me say a few words about the Cantor set. So Cantor sets support natural measures. You get them by just distributing mass 1 from the initial terms, and you distribute it evenly among the recursive construction, and this gives rise to a limiting measure. And if you Fourier transform this measure that comes out of the middle third Cantor set, normalized by 2 pi, for convenience, you get this horrible product. Now, I would like to know if certain metrical results hold for the Cantor set. If I restrict to this thing. Now, I can't do anything about these results because if you look at that guy, it does not. That's going on. It's even worse. You can't even get a measure in which the Fourier transform decays. The result can. Okay. So can I get something which resembles it? Here's a Cantor set which almost works. So instead of removing the third, I remove excited part. And I can do a Cantor measure construction as usual. So for any side between 0 and 1. Probably sometime in the 60s, I couldn't find an exact reference for this. Salem and Simon proved that you have to carry a Fourier transform. Unless the inverse of psi happens to be Peugeot number. So Peugeot numbers, I recall, were introduced yesterday in Victoria. Algebraic integers bigger than 1 whose conjugates or less than 1 modules. And this is an if and only if. This falls just short of me being able to apply it. I get decay, but I don't know how much. And if I knew how much it decayed, I could say so. Let's do something else. Let's pick various parameters. And pick some random variables uniformly distributed. This is a construction of Bloom. And then what I do is, I take a bunch of random variables and define a random candidate. So what's happening is, I'm wiggling the bit that I take out randomly. Okay? So following some random process at each step for each interval, I just wiggle the things. This gives me an awful lot of things. There are now random variables. And you can calculate the Fourier transform of the resulting measure almost surely. That's what it is. It's as big as it gets. So almost surely these things are Salem sets, which is very annoying. Because those are all the sets that I'm not interested in. I can't tell you what's in there. They're random. So everything I've done so far, I could just apply to measures on these guys, right? So here's a challenge for you all to find an interesting example of a Cantor set which is arithmetically interesting, such as the Fourier transform decay. I've told you can't use Peugeot numbers. That would be wrong. Okay, so what was I interested in? There's a result of castles, which looks at the Cantor middle third set. If you look at the nx, and we take the discrepancy as this. This is little over n. Mu Cantor almost surely. Right? That's the result of Cantor. So I wanted to say something slightly bigger. But if the Fourier dimension of the Cantors that I'm looking at is positive, this is true. Okay? Well, it'd be natural to ask, evidently, numbers in the Cantor set are not normal to base 3, but if you take a divisibility sequence where all the primes involved are either 2 or 5, would the same thing be true? And you have a lot more flexibility, or very often. This seems true for almost all Cantor sets, or random, but I don't know it for the middle third Cantor set. This annoys me. This is the open problem.